Welcome everybody to today's lecture. Today we're going to be looking at recursion. Typically at this point in the semester I like to talk about casting and recursion. I am going to cut out the casting talk just because we're running on a shorter schedule than normal. The summer terms are a few weeks shorter than the spring and fall terms. So we got to make room somewhere, and that's just something we'll drop. It's definitely an important concept and something that you need to understand at some point. So I'd encourage you to look it up in the book and read through it. Of course, if you have any questions, you can email me and I'd be more than happy to talk about it. With that then, the focus of today's lecture will be on recursion. I'm going to try to keep it short, but recursion is a somewhat complex subject, and so this might be a kind of a long lecture. Before we get into that though, I do want to take a minute and just walk through what is essentially a Lab 2 solution. With programming, my experience as a programmer for the past few years is that there are a lot of different ways to solve it. To solve any problem, to write any code. And so I try not to get too hung up on any one person's particular decision or process for solving. So this is just my proposal, just based off of how I'm trying to teach the course, and just all the code that I've looked at over the years. So this program you were supposed to enter in 7 temperatures and calculate a couple of things based off of that, the average, the high, and the low. So the first thing we do is declare an array, an integer array of size 7, and initialize it to 0. Okay, it's pretty important to do that. I always define function prototypes because I define those function prototypes before my main. Then I don't need to worry about implementing my functions until after main. So you can see here that I'm going to have 3 functions that return an integer value, and then they have 2 arguments. The first one is an array, and the second one is an integer value that will represent the size. So if you struggled with how to declare an array as a function argument, this is how you do it. The type, the name, and then the square brackets. You don't need to define a size here. Moving on, then I just print off something to say enter 7 temperatures, and I go through a loop 7 times. Okay, pretty straightforward. I do want to point out that if you wanted to, you could do something like, and you could create, you could have 7 of those format specifiers for a numeric value, and then whatever your array is, temperature at I, or no, I'm sorry, at 0, you have to use an actual index value. And you could repeat this, this format then, and that would allow the user to enter in 7 numeric values on one line. They'd have to enter it in that exact format, numeric value, space, numeric value, space, numeric value. But it is possible. So however you decided to do that, that's fine, as long as you worked, as long as it captures 7 values and put them in an array. From there, once I have those 7 values in the array, I declare 3 variables, and I assign the return value from those 3 function calls to those variables. So pretty obvious variable name would be average, high, and low. I declare variables instead of just calling those functions in the condition themselves, because I need to use those variables, the values from those function calls, several times in the program. And you'll see here in these if statements that, well, not only do I print them, but then I use them in the conditions of the if statements. And so I use them over and over again. And I didn't want to have to call the function over and over again because in general, I try to minimize my function calls. And if that means I need to store a function's return value in a variable, then that's what I do. If that value is going to change a lot, then either I just call the function a number of times, or I simply call it and update the value that I stored in that variable. So in this case, I only need to calculate the average ones, the high ones, and the low ones, and then I can use that result over and over again on the rest of this program. So we'll look at average temperature, highest temperature, and lowest temperature here in turn. So we move down, and here's our average temperature. Okay, declare a loop. We iterate over every single element of the array. We add those values into a total variable and then return the total divided by the size. Okay, since size is an argument for my function, size is the size of the array. So I just use that to not only define the condition here, but also to divide by the total or the sum. All right, as far as highest temperature and lowest temperature, they're pretty much identical except the condition. So what I do is I first declare my counter variable. I next then declare a variable that I'm going to store the highest value. We need to move through every single element of the array, and with each pass we need to be able to compare what's the highest value I've seen with the value that I'm currently looking at. If the one I'm looking at is higher than the highest I've seen, I need to update that value. And we need to keep track of that. And so the easiest way to do that is to declare a variable. Instead of initializing this to 0, I actually initialize it to the value of the first element of the array. And the reason I do this is because then high always has a value that is part of the actual array. So if my very first temperature entered was my high value, it's already been assigned to high, and that's the value that will ultimately be returned. Some other options would be to say int high equals 0, right? And you'd initialize that value right away. But the problem with that would be, what if all the values in your array were negative values? What if for some reason Apple decides to build a manufacturing plant in the tundra, right? And so if that's the case, if every single value in that array was less than 0, then we'd have a faulty function. It would return 0 when in fact it shouldn't. It should return something else. And you could say the same on the other end. You could also, I've seen it done before, where you define some, just arbitrarily high number like this. Well, I'm sorry, some arbitrarily low number. We're looking at the high function. And then knowing or just assuming that no one's going to pass a value in or put a value in that array that's lower than that. They're all going to be higher, so your first iteration will assign a new value. And that works, but I think this is just a much cleaner solution. So that's what I did. Once I define that or set that initial value to the first element, then I just skip that element in my loop, so we can start right away at I equals 1. So we compare element 2 to element 0 essentially. And if this one is higher than that, then I have a new high. Set that value. Once this loop finishes, then we'll return the value of high. Okay. Low is the same way. I just switch the condition. So here I'm looking for greater than. Now I'm looking at less than. Okay, and I initialize the low variable in the same fashion. All right, finally, I have those values. They're stored in these variables, average, high, and low. I print the average, the high, and the low, and then I print off my warnings. Okay, in the lab I said print off warnings for all 3 computed values, the average, the high, and the low. And you really should probably check both bounds for every single value. Again, is it likely that's going to happen? Is it even feasible that those temperatures on Earth exist for a place to have a high, an average, a high, and a low, or an average of 113? I don't know. But I want my program to work. I want it to be comprehensive. And so what I do then is I compare if average is greater than and less than. So, or I'm sorry, greater than or less than. If it's either one of those, it's outside of the recommended ranges. And if you get into finer detail to say, oh, it's higher than or it's lower than, that's great. Same with the high. Important thing is here that I'm comparing it. You could, like I said, you could use an else if. If high is greater than 113, print it's too high. Else, if high is less than -4, print it's too cold. Important thing is to do all 3, check all 3. So I think everybody did well. So if you have any questions on that and you did not get it, I didn't provide adequate feedback for you, just let me know. I'd be more than happy to discuss it further. So, all right, that was lab 2. Let's check our timer. All right, so let's move in. That won't go away. Let's go ahead then and move into recursion. So recursion can become a very complex subject. And if you're reading along in the book, we actually have to jump back to section 5.15 in the book, so chapter 5, to even have any sort of talk about, nope, I take that back, it's not 5.15, it's 5.14. And so you have to jump back to chapter 5 to even talk about recursion. So at this point, I'm assuming that you did not cover recursion in 150. That's oftentimes the case, but I can't say that it's every time. So I'm assuming that you haven't. If you have, great. Hopefully this is more or less a review for you. If you haven't, then this can become a struggle for a lot of students. I know the first time I dealt with recursion, it kind of blew my mind, and I really didn't understand it even after I finished working on the labs that I had that were based on recursion. With that in general, I'd like to say for everyone to don't get discouraged if you're taking a what can be a very challenging course if you're early into programming and you're doing it online as well. And online provides a whole new set of challenges that you just don't have to deal with when you're taking something on campus. The large one being that you don't have the ability to stop me in the middle of my lecture and say, hey, what you just said doesn't make any sense. I need you to explain that again. Or to wait after class and sit down and go through this stuff 2 or 3 or 4 times in a single week. I know it's more challenging. But don't get discouraged, and don't get discouraged with recursion and anything else we talk about this semester. This is still more or less an introduction to all these concepts, and so I'm just looking largely for that you're putting effort into the course. If you're acing it and you're not having any problems, then that's great, and you can let me know, and I can try to provide you with more of a challenge. But if you're not, don't get discouraged. My 250 experience when I was in college, did my undergrad. I have a bachelor's in computer science. By the end of my 250 experience, I was really doubting my decision to go down this career path. I really didn't enjoy my 150, 250, and I really didn't feel like I learned a whole lot when I got done with 250. I just felt like I was overwhelmed and more or less confused on everything. I stuck it out though, and I've been programming ever since, and I really, really enjoy programming and all the opportunities it has provided for me over the years. So, if you just absolutely can't stand it and you're just going to get through this to get through it for your program, then great. But again, I just want to say, don't get discouraged. This may be a tough subject, but we'll all get through it. So, anyways, let's get into recursion then. So, up until this point, again, assuming that you haven't looked at recursion yet, most if not all of our programs have been structured in a very hierarchical manner. That is, we enter into our programs through the main function. We maybe have some custom functions or functions from other libraries that we include. We call those libraries. Our program execution begins. We call those functions. And from another function, once that function is done, it returns and our program moves on. For the most part, we've had a combination of those custom functions and functions from other libraries, and we call one function out of main. That function is called and it returns. We go back to main, and then our execution moves on. And this is great, but at some point in time, it's very, very handy to have a function that's able to call itself, and that is where recursion comes in. So the simple way of looking at recursion is that it's a function that can call itself an undetermined number of times until it solves some problem, and then it starts to finally return. Okay, so a recursive function calls itself. That's what you need to go. Keep in mind, okay, this can become a very complex subject. It can be very intimidating the first time you look at it. This is an intro, and so we're going to walk through. I am actually going to use I think I'm using an example out of the book. Yep, I'm using an example out of the book. So read the chapter, read the section, look at the code I'll provide. The lab itself will be very similar to the code that we're looking at here. Okay, so again, it's just an introduction. So don't expect yourself to maybe even fully understand what you did to figure out the lab, and certainly don't expect to be a recursive expert by the time we get done with this. The other thing, while I'm talking about all this high-level stuff, I often find students we'll get through this lecture, we'll talk through the code samples, and you'll think, oh, this isn't so bad, this really makes sense. And then you actually sit down and try to write the program, and you have a hard time coming up with a clear path or a clear idea of what exactly to do. And so, again, just go back to the example, go back to the code, work through the recursive function, how they work, and hopefully that should help. And again, send me an email, ask me questions. If the lab something isn't making sense, you have to let me know. I don't know that. I don't have the ability to kind of measure facial expressions and interactivity because we don't have that, obviously. So you have to let me know. So conceptually then, if a recursive function calls itself, then how do we structure a recursive function? Well, all recursive functions are designed to solve what we call the base case, and this is the simplest case. So we create a recursive function, a function that calls itself over and over again, because we want it to solve a complex problem, break it down into something that's simple. When it reaches that simple, that's the base case, it can stop calling itself recursively and start returning. Okay? It's a recursive function, so it's no different in that you call that function and that function will ultimately return. Okay, and we'll see how that's structured here when we look through the code example. There's kind of two paths we have to look at when we create our recursive functions when we call them. If we call a recursive function with the base case, then it simply returns the result. It doesn't call itself recursively. If you do not call that function a recursive function with the base case, then it has to break whatever problem you presented it with into two conceptual pieces. The first piece is essentially the base case. It's something that it knows, well, I take that, it's not the base case, but it's something that it knows what to do with. The second piece is what it doesn't know what to do with, and then it calls itself recursively in an effort to break that problem down to eventually get to the base case. Okay, with each time we break it down, each time you have a recursive call, the problem becomes a little less complex. We're trying to converge on the base case, and so we take the problem and we break it down. We call ourselves recursively. If we not reach the base case, we break it down again. We call ourselves recursively. If we haven't reached the base case, we do that again. We do that until the problem becomes simple enough to be solved. Each time we break that problem down and do a recursive call, we call that the recursive call, the recursive step. One thing that you have to keep in mind is, and this is hard to depict, and I think it's a little hard to understand until you've just worked through recursion. So, bear with me on this. But when a function calls, let's look at a snippet from the Lab 2 solution. So let's say that we execute this program, and we know that C is a procedural language, and so execution enters into the program, and we procedurally start executing lines of code essentially from the top to the bottom. When we get to this point right here, and hopefully I can not scribble, I can make coherent arrows and things here. When we get to, let's say that our execution is now on line 20, and we're trying to evaluate this assignment, right? And we have a function call. So we see that average temp is a function call. So the execution of the program pauses and passes to this function call right here, average temperature. Now I don't have all the I don't have the screen capture big enough to see all that, but now our execution in main is holding right here while we execute that function. We do whatever code is inside that function until we hit a return. Once it returns, okay, execution comes back to here. We assign the value to average, and now execution can move on. So we went from here, now we're right to here. And then we repeat that over. Okay, the important thing is that every time we call a function, execution from the function that's calling waits as the function that calls returns. So you need to keep that in mind, because when we look at the recursive function, it does the same thing, except that it's waiting, the function itself is waiting on itself, essentially. Recursive, okay, there's the potential that you can create a recursive function that never returns. That's bad. That's essentially an infinite loop. But for the most part, our recursive functions, we don't necessarily know how many times they're going to be called. When you create a recursive function, you don't say this recursive function would be called 10 times every time. That's not usually the purpose of a recursive function. It's to say this function will be called recursively until it reaches the base case. And I don't know what that is until I know what the input is. All right, we reach that base case. Okay, again, base case. Okay, that's one of the key terms for us. When we reach the base case, the result is returned. Okay, this means that the function stops calling itself recursively and it starts to return. All right, so there's that sample code. All right, so to look at a recursive function, we're going to look at the factorial problem that the book talks about. In case you haven't worked with factorials, this is the format. This is how we write a factorial. It's the number and then an exclamation point. A factorial is simply it's this pattern. It's the number times the number minus 1 times the number minus 2 until we get to, oops, I'm not sure what I did there, sorry about that, until we get to the value of 1. Okay, so if let's say we did 5 factorial, it would just be 5 times 4 times 3 times 2 times 1. Now, if we look at that in the terms of, let's use this as an example to set up a recursive function, then we need to create a function that takes, this is the problem. Gosh, This is harder than you'd think to write. That takes a problem. In this case, it's let's solve the factorial for a number, for an integer value, a positive integer value, and let's break it down. Okay, this is the base case. If I call that function, if I call a factorial function and I provide my argument is the value of 1, then we've reached the base case. This is what we return. We return a value of 1. If I don't, then we need to take that complex problem and break it down into something simple. So this is the format that we use in order to break it down. Itself times itself minus 1 times itself minus 2 until we reach the base case. So this, using factorials, we're going to look at a recursive function. All right, and this is it. This is the program. So we're going to look at it here in PowerPoint just so I can write all over it. And then after that, we'll actually look at the program just real quick in code and we'll execute it so you can see it run. There's a couple of things you don't really need to worry about. Okay, don't get distracted with this unsigned long int. With factorials, factorials can get large really, really quickly. And this value here, first of all, probably should talk about it if I don't think I've mentioned it before. But in case you don't know, the difference between signed and unsigned, signed means it can be positive or negative. It can have a sign. Unsigned means that it's positive only. And when we're dealing with factorials, we're only dealing with positives. It is an integer, and then long just essentially allocates more memory for the variable itself. So don't worry about those. All it means is we're going to have really large values. All right, so this program has main and one custom function. That custom function is the factorial. You can see we have one argument. It's an integer number. By saying that this is an unsigned integer number, that means that that function will not accept any negative values. Okay, so that's all the reason. That's the only reason we're doing that. There we go. Inside main, then I'm going to declare one loop. This loop's going to go from 0 to I is less than 10, so we'll have 10 iterations, and we're going to have one printf. And again, don't let all this stuff here confuse you or cause you any concern. This is simply a format specifier for a numeric. That's just going to be an exclamation point. So when you see the output of this program, it's going to say, oh, that's 0 factorial, 1 factorial, 2 factorial, dash \t, that's just inserting 2 tab characters, so that's just going to help keep our output aligned. %LLI, okay, that's just our percent, that's just long int, so that's matching up with the return value, the return type of our function here, and then a new line. So then we're going to print the value of I because that's what we're going to factor, and then for the second argument to our printf, we're going to provide the return value from the factorial call to this format specifier here. Okay. All right, get rid of all that. So let's look at the function now. Surprisingly simple. We have to structure it to solve the base case. Okay. If we go back and look at this, I said the base case is 1. When we've reached 1, then we know we've solved the problem. We've solved factoring some number. So that's what we're doing with this first branch of logic. Return 1. If number is less than or equal to 1, return 1. This is our base case. If it's not 1, then what do? Well, we use this, we create a recursive step. So if we go back to the slide, we have, back one slide, we have this process right here. Right, n times n minus 1 times n minus 2 until we've reached a value of 1. So how do we do that? Well, we take the number and we multiply it by the recursive call, factorial of number minus 1. This isn't number minus 1, then number minus 2, then number minus 3, because every time we call this recursively, this value is 1 less. Okay, so in the very first instance, we'll have 5, assuming that we're factoring 5 times the factorial of 5 minus 1. So what is that recursive call? Well, it's 4. All right, and I'll go through this a little better here in just a second. So the important thing is that we identified this as, yikes, our recursive step. Okay, this right here is our recursive step. This is that formula. This is that way of taking something we know with what to do and breaking it down, breaking that problem down into something we still don't quite understand. Our goal is to get to the point where number is less than or equal to 1. So what happened? Hopefully this helps to kind of clarify what I was talking about there. Let's say we're trying to solve 5 factorial. So we're going to start right here. Using that example, using that code, think about that function now as we're walking through this. We need to reach the base case. The base case is when n is equal to 1. All right, so right down here, I'll get rid of that. This is our base case. We're happy when we get here. But right now we're at 5. So looking back at that function, what do? Well, we say number times the factorial of number minus 1. So that's like saying 5 times 4. All right, so now 4 gets called recursively. The factorial function receives 4. It checks. Is 4 less than or equal to 1? No, it's not. Well, we need another recursive step. So what do? Well, we call itself recursively. We say 4 times n minus 1, or 4 minus 1. So 3. Okay, so again, factorial function is called. Okay, and keep in mind this whole time, right, program execution is paused. We call the recursive function initially right here, and then it has to wait as each individual function call is called and then eventually starts to return. Okay, so 4 times 3. So recursive call, we have a recursive step, and what do? The function does the first condition of that if statement and says, is the number, which is the value 3, is that less than or equal to 1? At this point it's not, so another recursive call. So we have n, or 3 minus 1, which is 2. So here's our next recursive step. We take the value 2, and we say, is it less than or equal to 1? Still not, so we have another recursive call. We take 2 times 2 minus 1. So recursive call, and we have finally the value of 1. Is number less than or equal to 1? In this case it is. And now we start returning all the way back up until we get to that original function call that started all of these recursive calls. Okay, at this point we return back to here, and now execution of our program can continue on. There's no more recursion. So what does it do when it starts to return? When we reach that base case, we start to return. We return 1, right? That's the very first thing we do. And since the recursive call that got us to this condition was 2 times 1, we return 1 to here, and now we multiply. Okay, let's say we go back and actually, yeah, I'll try to erase this all here. It's only slightly legible anyway. Okay, so when we have an equation like this, we have order of precedence, and what we're trying to do is we want to do some arithmetic operation. We have a value on the left and a value on the right. Before we can do the arithmetic operation, because this is a function call, we have to call the function. We have to evaluate the function. So until this function call returns a value, we can't do the multiplication. This now, because when we reach the base case, that starts the return chain. Every recursive function call can now return. So now that we can return, we can take the value that's returned by that function call and multiply it by the number. Okay, so we return 1. To get to this condition, we had 2 times 1, so now we can multiply 2 times 1. Now we have a value of 2. To get to this recursive call, we had 3, so 2 is returned here, and now we have 3 times 2. Okay, and we just keep doing that. 2 is returned. We keep doing that, sorry, all the way until we return 120. 120 is 5 factorial. Okay, and this is kind of my attempt to depict this in code. You know, if we were looking at just that one block, bear with me here, if we were just looking at this function call, that section of code here, this is what it would look like. When we start with 5 factorial, and then we have 5 times a function call, the factorial call, and the value of 4, so 5 minus 1. 4 times factorial, 4 minus 1 is 3. 3 times factorial, 3 minus 1 is 2. 2 times factorial, 1, 2 minus 1, which is 1. And we return up. Okay, so this is just looking at that return process, but starting here. And then we have 2 times 1, 3 times 2, 4 times 6, and 5 times 24. All right, 2 times 1 is 2, it's returned here. 2 times 3 is 6, it's returned here. 4 times 6 is 24, returned here. So 5 times 24 is 120, or 5 factorial. Okay, I already talked about that, so just keep in mind, if you decide to modify the program and do values greater than about 20 or 21 there, you may run into problems, run out of memory or something, I don't know. Give it a shot if you want to do it in the IALab. The IALab's a pretty safe place to do it. Worst thing you can do is have to power cycle your VM. If you're doing it on your own machine, probably the worst thing you'd have to do is kill VMware Player and start over VirtualBox, whatever you're using. Alright, so here's the program. Alright, everything that we just talked about, same program. So I'll provide you with an example, same example in the book. So what do we do? Okay, every iteration of the loop, we call the factorial and the value of I. Right, so this is that first call. If we go back here a couple slides, that's this call right here. Right, that's the first call that kind of sets off this whole chain of recursive function calls. Okay, so that does it. If we have a value of 5, and that's what we're calling, then we'd enter into this function and we check. Okay, if this is 5 less than or equal to 1? No, it's not. So let's return, and then we have another function call, the recursive step. Okay, we just talked about this can't return until we've reached the base case. Okay, and as we call this recursively, execution is going to hold here as we call factorial again. And we'll call factorial with a value of 4. And then we'll call it with a value of 3, then 2, then 1, and then finally it can return. This returns, and now we have a value, and we can multiply it by the number until we return all the way back to the original function call. So let's take a look at that. Go ahead and discard those. Take a look at the program. Not a whole lot to it now. We've been through it. I will have this annotated. So base case and the recursive step. If we compile that, which I already did, so we'll just run it, and you can see here 5 factorial is 120. So let's see. Well, that's really it. All right, so that's recursion. What I will encourage you to do then, there'll be one more lecture, and that'll talk about the lab will be to convert a essentially an integer value into a binary number, and that shouldn't be maybe sounds a little scary, but it's really not. I'll talk through that in the next lecture. How to do the conversion. Or at least how to do it conceptually. The challenge will be to design a function that does it recursively, and then I'll also show you. We'll walk through I'll provide a template more or less for this lab, so that you don't have to. You only have to focus on writing the recursive function. Again, if this doesn't really make a whole lot of sense yet, or you're a little confused, I would encourage you to first run this program, work through it, start working on the lab, and then again, feel free to ask me questions. I will provide the practice labs as well, or I'll try to make some up. There isn't much in the book for recursion, so I'll try to come up with something, and that should help you out. So, but again, bottom line, if you're struggling with it, let me know, and I can help you out with it. So that's it for lecture. Thanks.